Greetings and welcome to the Chemistry 222 lecture for Chapter 20, which I call the Organic Chemistry chapter. And I think it's really nice that you're here, and let's see if we can figure out some organic chemistry. First, a quick word, though, about why we're skipping chapters. Like we just finished Chapter 7 and 8, and we'll do 9 here after this chapter. But Chapter 20 goes along really well with the previous chapters. It's mostly about organic chemistry. And organic chemistry involves a lot of geometry, so we'll see lots of tetrahedral arrangements of atoms. For example, the molecule shown there at the bottom of the screen, all of those, I think anyway, they're carbon atoms would be in a kind of a tetrahedral arrangement. We'll also talk about geometry, see the effects of hybridization and stuff like that along the way. On a personal level, though, I wish to talk also why this chapter is so important to me. When I finished the Chemistry 221 through Chemistry 223 equivalents at the college I went to, I was feeling very confident about chemistry. And I thought, oh yeah, I've got all this stuff down, no problem. And I went to organic chemistry and I said, oh yeah, I'm going to rock it. And needless to say, the first quarter of my organic chemistry class, which by the way, that's the second year chemistry class after this series is done. The first quarter of organic chemistry really knocked me on my bottom. And I was really surprised. And some things that I thought were different were actually the same. And some things that I thought were the same were actually different. For example, there are many classes of compounds we're going to see that sound very similar to each other. An alkane and an alkene are different, for example, and that's something I hadn't heard before. It didn't help that my instructor at the time had a little bit of an accent, and I thought, oh, well, it's just the accent talking. Well, no, it was me not knowing what was going on. So when I started to teach chemistry at Mount Hood Community College, it was almost my goal to prevent my students from having the experience that I did when I went into organic chemistry. I wish for you to be prepared and know that an alkene is different than an alkane, which is different from an alkyne. All these names sound kind of familiar. I don't want you to have the bad experience that I had. I want you to enter into organic chemistry strong. If you aren't planning on taking organic chemistry, and there's a lot of you, I'm sure, that are not, this chapter will still have a lot of use to you because a lot of the things around us that we use are actually organic chemicals. And knowing how they're named, you can kind of figure out what it is. I think it's really good as a citizen of the world to be prepared and to know what's going on. So for all of these reasons and stuff, then, I think this is going to be a good chapter, and I'm really glad to have you here. So without further ado, let's go into organic chemistry, talk about what it is. If you're going to take it, hopefully you'll be better prepared after this, and if you're not, you're going to learn a lot about OChem and the things around us which you may not have thought about before. Pretty cool. Organic chemistry basically is most of chemistry in general. There's something like over 20 million known compounds, and most of them, by all means, are based on carbon, all right? And organic chemicals are basically compounds based on carbon, and there's a lot of them around us. So my beloved caffeine, vitamin C, whole aspirin, all these kind of things and stuff are basically organic chemistry. Now, carbon is, as we saw in the last couple chapters, limited to 4 bonds around it, the octet rule, all right? It's never going to have more than 5. So we won't see like trigonal bipyramid and octahedral in this chapter, but we are going to see a lot of tetrahedral, trigonal planar, that kind of stuff. Most of organic chemicals then have carbon and hydrogen. A lot of them have oxygen as well, nitrogen sometimes sulfur and stuff. And there's a whole bunch of variety of compounds. And on this slide, you're seeing some of the possibilities. The animation there in the middle right is benzene. Benzene is a truly unique compound compared to the stuff we've seen so far, and we'll talk more about what it is. The lower right corner there, that's called propellerine. You can see it kind of looks like a propeller and stuff like that. So that's kind of interesting. And the rotating molecule in the lower left, that's actually propane. So if you've ever had a barbecue, you're probably using propane for your barbecue. Lots and lots of examples of these things. In organic chemistry, there's two main areas that people focus on in the major level course. And remember that this is a year-long course, all right, in the after Chem 223. So we're just going to barely dip our toe into this area and see what's going on. But anyway, when you think about organic chemistry, there's two main areas. Nomenclature is the big part. And nomenclature, like we saw in Chem 221, is just being able to name the compounds. So nomenclature of organic chemistry is going to be a big part of organic chemistry. You have to know what you're talking about, know which chemical to ask for, stuff like that. The other part of organic chemistry that's big is the reactivity. Like, what do you do with the compounds once you've made them? How do you make the compounds? Stuff like that. And those are really good. So in this class, in Chem 222, we're going to focus more on the nomenclature than anything else. So I want you to know the names. So know, again, like I said earlier, that an alkane is different than an alkene, stuff like that. But I will show a couple of examples of reactivity just so you kind of get a feel for the things that are out there. And then in the real organic chemistry year-long class, you'll go into a lot more detail about how the chemicals react, how you make them, stuff like that. When it comes to the naming of organic chemistry, you must start at what's called the alkyl groups. And alkyl groups are like building blocks for making organic chemistry compounds. Alkyl groups are not compounds by themselves. You have to add something to them to make them a compound. But these alkyl groups are in everything, and a lot of the naming we're going to do is based on the alkyl group. So I do encourage you to pay attention. One we've seen a little bit already in these lectures anyway, is the methyl group. Now, a methyl group is a tetrahedral sp3 carbon with 3 hydrogens connected to it. So if you think about what that is, tetrahedral means 4 bonds. CH3 has 3 bonds to hydrogen, but there's like 1 bond left over. So you can imagine then that I could draw here a CH3, and there would be 3 H's, but there'd be something else. And this something else, you can add different pieces to it to make it a compound. CH3 by itself is not a compound. That carbon needs 4 bonds. It needs an octet around it. But you could have a hydrogen next to it, or you could put a chlorine there, or an oxygen, stuff like that. So a methyl group is the simplest of the alkyl groups, and we're going to talk about it a lot. And a methyl group is just one sp3 tetrahedral carbon. The second alkyl group that we'll run into a lot is called an ethyl group. Now, an ethyl group is nothing more than a methyl group with a second tetrahedral carbon. So let me erase that question mark I put up there for the methyl group. And an ethyl group is nothing more than another tetrahedral carbon connected to the methyl group. So just like the methyl group, an ethyl group is not a compound unto itself. That should be a hydrogen. Sorry, that's really sloppy. There's something else that has to go there to make it a compound, and you could put a hydrogen there, oxygen, nitrogen, whatever. So an ethyl group is just a building block of organic chemistry. Ethyl has 2 carbons, methyl has just 1. Propyl is the next of the alkyl groups. So if you put another tetrahedral carbon on the end of the ethyl group where my question mark is, that would then essentially build you a propyl group. You'd still have another spot left over to put another group in there, and a propyl group is not, again, a compound. It's just a building block. Notice, though, how earlier I mentioned propane. Propane is related to propyl group, and we'll talk about that in a little bit. Butyl is 4 carbons, and again, all those carbons are tetrahedral sp3, so you'd have something else on the end of the butyl group there to make it a compound. A butyl group is not a compound unto itself. Then there's also pentyl, hexyl, heptyl, octyl, which are 5, 6, 7, and 8 carbons. Yes, it goes beyond octyl. There's nonyl and decyl, which are 9 and 10, etc., etc. We're going to see that using an R is a helpful term here. And R just means you have some generic alkyl group connected to it. So if you see a big R, it just means you could have a methyl group, you could have an ethyl group, all kinds of stuff. Alkyl groups may be combined with other elements or other alkyl groups to give classes of compounds. So you're going to see that organic chemistry is split into different types of compounds or classes, all right? The alkyl groups are the building block. So you could put two methyls together, for example, or you could put a methyl and an ethyl, or a propyl and a butyl, or anything like that. You could also combine them with hydrogen and chlorine and a whole bunch of different things. At this point, I'd like to advertise the handout listed at the bottom, the Organic Chemistry Nomenclature Guide. This is in the companion. It's also on the website. But this lists many of the beginning alkyl groups in greater detail. And also, there's a whole list of the different families or classes of compounds that we're going to be seeing in this section. So I do recommend that you check out that handout to get a better idea as to what's going on here. So the simplest of the classes of organic chemicals is called an alkane. And an alkane is when you take a generic alkyl group R and you put a hydrogen on the end of it. So literally, like we said, all of those groups we saw, the alkyl groups, they aren't compounds, but if you put a hydrogen on the end, then your carbon has 4 bonds around it, it's got its octet, and you're going to make a compound. So all of the alkanes are just alkyl groups with a hydrogen on the end of it. There's a generic alkane formula. You can see it there. It's CnH2n plus 2. So for every n hydrogens, you're going to have 2n plus 2 hydrogens. And to name an alkane, you take the alkyl group, you subtract the YL, and you add ANE to the end of it. So let's look at the simplest alkane, which is methane. Methane comes from a methyl group. So if you take the YL off the methyl, you get meth, and it's not that kind of meth, all right? It's just a meth group. Anyway, add ANE to it, methane, that's where the name comes from. And notice the formula. For every n carbons, you have 2n plus 2 hydrogens. So we have 1 carbon, so 2 times 1 plus 2 would be 4 hydrogens. Methane is CH4. Methane is the main ingredient in natural gas. So if your house or home is heated by natural gas, then you've certainly used methane and stuff for heating, which is really cool. So again, methyl group plus hydrogen makes an alkane. Methyl minus YL plus ANE is methane, and the formula CnH2n plus 2. But this is just a class or family of compounds, and this R was methyl, but you don't have to use methyl. You could use ethyl. So ethyl minus YL plus ANE would be ethane, and an ethyl group plus a hydrogen would be the formula for ethane. So N carbons here is 2 because there's 2 carbons. 2 times 2 plus 2 is 6. C2H6 is the formula, and this is ethane. Notice again that this is all tetrahedral, sp3, all the bond angles are 109, etc., etc. Ethane is a small component, as I understand, of natural gas. Most of it is methane, but there's a little ethane in there as well. Propane is a propyl group plus hydrogen. So you can see how propyl ends up as propane if you add a hydrogen to it. So the propyl group was CH3CH2CH2, put a hydrogen on the end, everything's tetrahedral, sp3, 109 degrees, etc., etc. Propane is this one. Propane is the main ingredient a lot of times in barbecues. If you've used a barbecue, it's probably propane, which is cool. And again, you can see the formula. But again, why stop there? Next one, butane. Butane is a butyl group with 4 carbons with a hydrogen on the end. In this case, N of 4, which is 4 carbons. So 4 times 2 plus 2, 10 hydrogens. You've got the thing. All right. If you hear the term saturated hydrocarbons, that just means that every position around the carbon is saturated with hydrogen, like you only have hydrogen. You don't have any double bonds, we'll see, or you don't have an oxygen or something like that. So anyway, all the ones so far have been just an alkyl group with a hydrogen on the end of it, and you can see how to name them. Which of the following could be be an alkane? And this is the kind of question you might see. And you can see there's a whole bunch of different formulas there. Well, the way to answer this is to go back to the generic alkane formula. And if you have an alkane, then for every n carbons, you're going to have 2n plus 2 hydrogens. So if you look at number 1 right there, n would be 2. 2 times 2 plus 2, 6 is certainly not 4, so number 1 is not an alkane. Notice that number 1 and number 2 have a CnH2n relationship. So for every n carbons, you have 2n hydrogens, so neither one of those would be right. If you go to number 3, 14 is n, so 14 times 2, 28 plus 2, aha, H30. So number 3 sounds like it's an alkane. Number 4, certainly not. You don't have anywhere near enough hydrogens for that molecule. And the last one has oxygen, so that's not an alkane. We'll talk about oxygen later, but it's certainly not an alkane. Alkanes have just carbon and hydrogen. So only number 3 there is going to be an alkane, C14H30. The other ones are different kind of structures, and we'll look at some of those here in a little bit. The formula for butane was C4H10, all right? And butane, which is 4 carbons in a row, is definitely one of the structures for it. But the problem with the formula C4H10 is that you can make an isomer of it. And an isomer, same number of carbons and hydrogens, same formula, but it's structurally different. So notice the structure to the right. It's a 2-methylpropane, all right? And that also is 4 carbons and 10 hydrogens. However, as you can see, the structure is quite different. So what we need to talk about before we go any further in organic chemistry is the idea of the longest chain of carbon atoms, all right? Notice that in the structure on the left, we have 1, 2, 3, 4 carbons in a row, in a chain, all right? So the longest chain of carbon atoms there is 4 carbons, and 4 carbons is butyl, which would be butane, okay? That's where that comes from. If you just have carbons in a straight row, then it gets the N symbol. N stands for normal. So N-butane would be the 4 carbons in a row with hydrogens all around. N-pentane would be 5 carbons in a row with hydrogens all around. The structure on the right, if you think about the longest chain, quote unquote, you're going to get 3 carbons, 1, 2, 3. And so this has a longest chain of 3 carbons, which is a propane. And there is a methyl group off the second carbon. Remember that methyl is CH3. So this compound is 2-methylpropane, where the longest carbons are 3. A methyl group is not part of it. That's where these names come from. Now, you don't have to count 3 carbons like I just did there in the nice line. Maybe you looked at it as 1, 2, 3. That's another way to see the propane group, and the methyl group, which is the part I didn't circle, is on the right off the second carbon. So notice that you can get 2-methylpropane from this way of circling the atoms as well. And this is going to be an important trait for you to do. And finally, you could also circle the 3 carbons right there. That would be another propane. The methyl group is off the middle, or the second one, second methyl. So that would also be 2-methylpropane. As an organic chemist, you need to start thinking about how to find the longest chain of carbon atoms, all right? And I would try different ways. So initially I had them all along the axis right there, if you will. Then I kind of twisted them in the L shapes, and that's good to do. You should kind of think about this. The longest chain in organic chemistry is super important, and we'll talk about this more here in a little bit. So isomers is one of the ways that organic chemistry is quite different from the Chem 221 through Chem 223 series of classes. This is something that's not usually talked about that much, but I wanted to bring it up because this is something you will absolutely see both in the regular class and also in the real world. Pentane is 5 carbons, a pentyl group with a hydrogen on the end. And if they're all in a row, then you get to N-pentane, which we're going to start using now because there are isomers of pentane. Now, the formula for pentanes, N-pentane, C5H12. So all these 3 structures have 5 carbons and 12 hydrogens. But you can tell here that they're quite different, all right? So, for example, down here in the lower left, you have, depending on how you circle it, you're going to have 3 carbons in a row, the longest chain, which is propane, all right? And not circled in that chain, there's a methyl group, if you will, above and a methyl group below. So there are 2 methyl groups there. That would be a dimethyl propane. And the numbering, which we're going to talk more about here in a little bit, we're going to put numbers next to both of the methyl groups. So that would be 2,2-dimethyl propane. And we'll talk more about numbers. The one in the upper right definitely needs a comment. So first of all, the longest chain of carbon atoms is 4. And what I'm going to do is I'm going to circle these 4 right here. So that would be the butane part, the longest chain. And you can include the one above if you want to, it doesn't matter. But notice the name. If you count left to right, it would be 1, 2, 3, the methyl group would be off the 3rd carbon. So it might be tempting to write it as 3-methylbutane. However, if you start and count right to left, this would be 1, this carbon would be 2, 3, 4. So we have a choice here as an organic chemist to call this 3-methylbutane or 2-methylbutane. And in addition to the longest chain of carbon atoms, in organic chemistry, you always want to use the smallest number possible. So 2-methylbutane is the official name for this compound. If you said 3-methylbutane, organic chemists would look at you like you were saying something like, I ain't knowing what's going on. Like you know what they're saying, but it's so slangy and kind of lame. And anyway, in the official chemistry world, the smallest number is the way to go. So 2-methylbutane is the official name. Can they figure it out if you say 3-methylbutane? Absolutely, but the smallest number is big. So let me reiterate the importance of these last 2 pages here. The longest chain of carbon atoms, definitely important, and the second thing, smallest number possible.
Hexane is a covalently bonded molecule consisting of 6 carbon atoms and 14 hydrogen atoms. Each hydrogen atom forms 1 covalent bond, and each carbon atom forms 4 covalent bonds. These 20 atoms can be rearranged into 5 different compounds called structural isomers, each having slightly different properties. Notice how the boiling points of each isomer changes. Arranging the carbon atoms in a straight chain produces N-hexane. Moving the end carbon to the 2nd carbon position and rearranging hydrogens produces 2-methylpentane. Sliding the methyl group to the 3rd carbon position produces 3-methylpentane. Moving the methyl group to the 4th carbon position appears to make 4-methylpentane. But wait, rotating the molecule shows that it's identical to 2-methylpentane. Now, adding the end carbon to the 2nd carbon position produces 2,3-dimethylbutane. Moving the methyl group to the 2nd carbon position produces 2,2-dimethylbutane. Sliding both methyl groups to the 3rd carbon position appears to make 3,3-dimethylbutane. But wait again. Rotating the molecule shows it's identical to 2,2-dimethylbutane. These are the 5 isomers of hexane.
Isomers become incredibly important as organic chemistry gets a little bit more sophisticated. All of these 5 compounds are C6H14, so N of 6, and times 2, 12 plus 2, 14 hydrogens. So they're all C6H14. However, you can see that their boiling points were actually quite different. That has to do with polarity and things that we probably won't talk about as much in this class, but there are a lot of differences. So they are not the same compound. They do have different reactivities, and knowing which one it is really important. So one of the goals you should start having is being able to figure out how many isomers there are, and that's what we're going to start talking about and also look at in the organic chemistry lab. Remembering that longest chain, smallest number is really important. Up there in the upper left-hand corner, you can see an example of how this works out. So let's say that you were trying to name this compound. All right, no problem. You first want to circle the longest chain of carbon atoms, and you can see what's done. It's kind of started on the upper right-hand corner and then kind of twirled around underneath. You could have also started on the left-hand methyl, went to number 2, and then 3, 4, 5, 6, etc., etc. The goal, though, is to find the longest chain of carbon atoms. That's going to be the base. So because the longest chain of carbons is 6, that's going to be a hexane. But not in the hexane part that's circled is a methyl group. So now we have to think about the number that's going to be in front of the methyl hexane. You want to use the smallest number possible. So if you start at number 1, obviously you can see it's number 2, so 2-methylhexane. However, you could also start at carbon number 6. You could say, all right, this is 1, 2, 3, 4, 5. You could also call this 5-methylhexane, but that would be incorrect. You want the smallest number. 2 is smaller than 5. So this is where it gets really important. Longest chain, smallest number will help you get through organic chemistry a lot. So again, if you see a formula, you want to start by finding the longest chain of carbon atoms. And I would just circle it. And you can just go in one direction. You can't go backwards or anything like that. You want to circle as many as you can because that's going to be the base part of your name. Then you want to number the chain from the end nearest to the first substituent encountered. Substituent would be like the methyl group right there. And honestly, when you're learning, I would number it both ways. So you can see in the picture there, the numbers that were already there, 1, 2, 3, 4, 5, 6 are good, but count it from the other way because sometimes your pictures will be deceiving and it's easy to miss out on a smaller number if you don't count both ways, especially when you're learning it. The substituents that aren't part of the longest chain you put in front and they'll have numbers next to them, and the numbers relate to where they're connected to the alkyl chain, to the longest chain of carbons. So it's 2-methyl. And of course, if you have more than one, you can use a dimethyl, but each methyl group would have its own number. And if there is like a chloro and a methyl, you want to alphabetize because that's how chemists roll and stuff. So here's one that's a little bit more exciting, and you do want to list them alphabetically. So here's another molecule. Might say, hey, how would you name that? And again, the goal is to find the longest chain of carbon atoms. So if you do this, then the longest chain is this way. Technically, you could, I suppose, have something like this, but your naming would get really ugly that way. So as a practical point, I would recommend doing the lower one stuff. So I'm going to erase that. But anyway, this is a 7-carbon chain. Heptyl becomes heptane when it comes to an alkane. All right, so this is going to be a heptane base. And then in red there, you can see the different parts that aren't in the heptane ring. There's a methyl here, a methyl here, and a methyl here. So it's going to be 3 methyls or trimethyl. And CH2CH3 is an ethyl group. So ethyl comes before methyl, and you want to use the smallest numbers possible. So you can see right here, it would be a 3-ethyl, and then it would be 2,4,5-trimethylheptane. Now, I would always, again, especially when you're learning, number it the other way and just make sure that you get the smallest numbers. So instead of 7, we could call this 1, 6 would be 2, 3, 4 is the same, 5, 6, 7. So instead of the name that's given, you could call it a 5-ethyl, and instead of 2, 4, 5, you would have 3, 4, 6. So you can see that there are smaller numbers in the name that's given, and that's why that's a better name here for this. 3-ethyl 2,4,5-trimethylheptane is the better name than quote-unquote 5-ethyl 3,4,6-trimethylheptane. Again, the chemist can figure it out, but it's kind of like slang, and I'm trying to teach you the right way to do it. So when you get your PhD from MIT or something like that, you can stand proud. These are the things that keep me up at night as an instructor. But anyway, just put them all together, list them alphabetically, good to go. Let's say that we wanted to name this organic compound. All right. So first thing, figure out what the longest chain of carbon atoms is. And I mean, you can play with this, and I encourage you to circle things and stuff like that. But let's say you were starting out and you're like, oh yeah, no problem. This is the longest chain, 3 carbons. It's some kind of propane. Well, no, because that's not the longest chain. If you look, you can get a longer group of carbon atoms by circling these 4. And again, I circled the ones in the middle of the molecule, but you could also take the top one instead of the far right one, or the bottom one instead of the far right one. You'd have the same thing. So 4 carbons is a butane, and you have 2 methyl groups, 2 CH3s, not in the longest chain that I circled. So this is going to be a dimethyl butane, all right? The question now is, what's the numbers in front of them? Because the numbers are really important as well. If you start on the left and go right, which is what people in America do, because that's how we read, right? 1, 2, 3, 4. It looks like those 2 methyls are off the 3rd carbon, so you could call it a 3,3-dimethyl butane, all right? But again, you should absolutely double check and make sure that the other way of counting isn't better. And so what you can do is go 1, 2, 3, 4, and lo and behold, if you count right to left, it's a 2 carbon, so it would be 2,2-dimethylbutane. So when there's a choice between 2,2-dimethylbutane and 3,3-dimethylbutane, that smallest number always wins out. It's going to be answer B. So again, hopefully you're starting to see how this works. You circle the longest chain of carbon atoms, that's going to be the base, and then figure out the parts that aren't on the base, and you want to put them alphabetical, and definitely make sure you count both directions. 2,2-dimethyl would be a better name than 3,3-dimethyl. Also important in organic chemistry is being able to create a structure from a name. And at first, the names in organic chemistry can be kind of a trip. So let's go through an example. Let's say that I asked you to provide the structure for 2,2,4-trimethylpentane. And of course, that name is kind of crazy and stuff. And at first, it might be like, oh, it can't be done. Oh, trust me, it can. So anyway, let's see how you do it. So the first thing you want to do is you want to go to the end of the name. So in this case, that would be pentane. And pentane, as we talked about, is a 5-carbon alkane. So what I would do in that case then is literally just write with carbons. I would write carbons in a row. And you can see there what I did. I went 1, 2, 3, 4, 5 carbons, all connected by a single bond. Single bonds, of course, being more probable. I also put down a numbering system. Now, I usually read left to right because I am an English speaker. You could do right to left. It's not a problem. Either way is okay, but just make one system and stick with it. So I'm going to use 1 on the left and 5 on the right for this name. Now, before the pentane, there's a tri and there's a methyl. So you can see I'm kind of going right to left in the name. So tri, of course, is a Greek prefix for 3. So that means there are 3 methyl groups in addition to our pentane chain. Now, each methyl group is like a carbon. And to know where you put those 3 methyl groups, that's where the numbers come in. And notice there's a 2, and a 4. So we have 3 methyls total. That means that we're going to have 1 methyl group off the 2nd carbon. We're going to have a 2nd methyl group off the same carbon. Remember, carbon can have up to 4 bonds. Normally, it's populated with hydrogens, but in this case, this carbon is totally surrounded by other carbons. And then, of course, the last 4, we're going to put a methyl group right there. So 2, 2, 4 means put a methyl group in this case at each of those positions, 2, 2, and 4. And tri means three methyl groups. You could also have a 2,2,4 trichloro and put chlorines up there, something like that. But hopefully you get the idea. And then finally, if you'd like to, you're welcome to populate the remaining positions of carbon with hydrogen. Again, the name of the game is that carbon always wants to have 4 bonds total. So the ending carbons there definitely would have CH3s. This structure right here is a mixture of some hydrogens and atoms listed, as well as line structures. But again, you can see there's carbon number 1 right there. Carbon number 2 has the 2 methyl groups. Carbon 3 in the middle, 4 right there at the vertice, and 5. So good to go. So that's how you do it. It's pretty chill. Going right to left has helped me out quite a bit on these for what it's worth. Let's do an example of how this all works out. Here's an example where I'd like you to draw the structure 2,3,4 trimethylpentane, okay? And the answers are just silly, so don't worry about that. But again, what you would do, and try this yourself, you would start on the far right. This is another pentane, so that would be a 5-carbon system. And you would literally just write 1, 2, 3, 4, 5 carbons in a row. And then because you have numbers associated with this molecule, I would highly recommend numbering them. So I'll just go 1, 2, 3, 4, 5. And again, you could go right to left. It's no big deal. Trimethyl, again, means three methyl groups. But you can see the difference here is that these carbons now are of the second, third, and fourth carbons. So 2,3,4 trimethylpentane is actually different than 2,2,4 trimethylpentane, which we saw earlier. So this is the compound for 2,3,4 trimethylpentane, a little bit fancier than the version I drew, but same idea. And again, the name of the game, start on the far right at pentane in this case. That's the 5 carbons. If it was hexane, it would be 6, etc., etc. And I do recommend numbering them. Number them, and you'll use that numbering system then to find what doesn't fit in the longest chain. So in this case, that was 3 methyls at 2,3,4. In the previous example, 3 methyls at 2,2,4 should be no problem. Alkanes are essentially straight carbon chains, like you have just carbons in a row, but there's like, if you will, a beginning and an end. But there's nothing that says you can't take those end carbons and put them together because they're all tetrahedral. So you take off some hydrogens and make essentially a cyclic compound. So a cycloalkane is nothing more than an alkane with the end hydrogens pulled out, and you put those 2 carbons together. So you can see the different ways here that these things can be done. The simplest one is cyclopropane. So propane had a CH3, CH2, CH3. Well, if you take a hydrogen off the end carbons and make a triangle out of it, that becomes cyclopropane. And notice there the structure. This is very common in organic chemistry, where the vertices and the lines are where the carbons are, and you can see how there's lines to carbons showing, but the hydrogens are totally omitted. And this is very common in organic chemistry, and we'll see that more and more. So a triangle is also the symbol for cyclopropane, and you just have to realize that at each one of those vertices, you've got a carbon. Carbon always has to have 4 bonds, so because those carbons only have 2 bonds, 1 to each carbon, that means there's going to be invisible hydrogens off each one of them. So this is something else to get used to in the organic chemistry symbolism. The one to the left of that is cyclopentane. Again, pentane without the hydrogens on the end. And then cyclohexane would be the hexane without the hydrogens. And you can have cyclobutane and cycloheptane, etc., etc. Notice that the formula for cyclohexane is different than the formula for a regular alkane. A regular alkane was CnH2n plus 2, but because we've removed 2 hydrogens to make the cyclic compound, a cycloalkane is just CnH2n, and that can be kind of important for the things that are going on. So if someone gave you a formula now, you could, in theory, at least tell the difference between a cycloalkane and an alkane based on just the formula. So going back to the list we saw earlier, which of the following could be a cycloalkane? And again, the goal here is to find formula combinations where for every N carbons, you see 2 N hydrogens. So again, number 3, which was the answer for the previous problem, would not work here, because if you had 14 carbons and it was a cycloalkane, you'd expect to have twice that number, or 28 hydrogens. 30 hydrogens is too many, so that's not going to fly. And C7H8 doesn't have enough of anything, so that's not going to happen. There's no oxygen yet, so we can cancel out that one. However, the ones on the left, all right, it's not impossible, because you have, for example, in the first one, 2 carbons, so 2 times 2, 4 hydrogens. That's possible. The second one, N would be 5, so 5 times 2, 10 hydrogens. Both 1 and 2 fit the formula for a cycloalkane. However, if you're going to have a cyclic compound, all right, you have to have more than 2 atoms, all right? You can't make like a structure with a circle. You only have 2 points. You need 3 points to make a cycloalkane. The smallest cycloalkane is a cyclopropane with 3 carbons. C2H4 is not a cycloalkane. It's something different. So the only one that really follows the structure here is B. You could have a cyclopentane, absolutely, that would work. But you can't have C2H4. There's not enough carbons to make a cyclic compound. All right, you would have just a line, and that's not the same as a cyclic compound. Cool. Instead of putting a hydrogen on the end of an alkyl group, you can put a halogen on the end of an alkyl group as well. And that creates another family of compounds, or class of organic compounds, called an alkyl halide. And an alkyl halide is just an alkyl group with a halogen on the end. And so in this case, you'd have the generic symbol Rx, and X could be fluorine, chlorine, bromine, or iodide. So here's just some examples of how these things work. The first example there, if you had a methyl group and you put an iodine on the end of it, you'd still have tetrahedral sp3 carbon at 109 degrees, but you've got an iodine there. So in the old school way, this would be called methyl iodide, i.e. alkyl halide, so methyl group iodide, and that's fine. Sometimes, though, you'll also see this compound listed as iodomethane, and this is another thing we're going to see in this section. So CH4 is methane, and if you put an iodine on the end, it would be iodomethane. So methyl iodide and iodomethane refer to the same thing, and on a quiz or exam, you have 2 possibilities to win. Woohoo! You could call that methyl iodide or iodomethane, and I would be totally happy. The next one there, you've got 1, 2, 3 carbons, so it's a propane, and you have an iodine I off the middle or second carbon. So the one way to call this would be 2-iodopropane, where the 2-iodo means there's an iodine off the second carbon in a propane group. You could also call this 2-propyl iodide, which is the old way. And again, if you change the iodine for a bromine, you would have 2-bromopropane. And if you put chlorine in there, it would be 2-chloropropane. So there's lots and lots and lots of possibilities. These types of compounds show up a lot in organic chemistry, so you'll see them, and you will see both ways of naming them, so just FYI. But in our Chem 222 class, where we're just introducing it, I'm happy with either way. You're good to go. Does this rag smell like chloroform to you? I put this on here for a silly joke. So the chloroform is what people sometimes use to knock someone out, and chloroform is an alkyl halide. It's CHCl3. So again, my weird sense of humor is popping up again. But anyway, chloroform, if you've ever seen, like in the old black and white movies, sometimes they put this rag over your face, then people go, oh, and they fall, they go unconscious. All right, well, anyway, it's chloroform, trichloromethane. I know, get a life, Michael. All of this may make you want to drink. I mean, just say no, kids. I mean, especially if you're under 21, 19 in Canada. But no, seriously, an alcohol in my world is not just the drinking alcohol like beer and wine and stuff like that. An alcohol is actually a family of compounds. It's a whole class of compounds in organic chemistry. If you take those alkyl groups R and you put an OH on the end of them, that's what an alcohol is. And alcohols are really useful when it comes to organic chemistry, not just to lament the hard studying you have to do, et cetera, et cetera. Anyway, it's pretty chill to name them. If you have the alkyl group, you take the YL off the name and you add anol. So you can see down there is an example of ethanol. Ethyl was the alkyl group, 2 carbons. Take the YL off for eth, then add anol, ethanol. And the formula CnH2n plus 2O. So notice that it's kind of like an alkane with an oxygen on the end of it. That oxygen is tetrahedral / bent sp3. So, and you can see it rotating down there. So you just add basically an oxygen between the other atoms to make it. Pretty chill. Ethanol is definitely the one that's consumed a lot in the United States with drinking, but there are actually a lot of synthetic reasons why ethanol is good for the lab. It's a really good solvent sometimes for making organic chemicals, so there's a lot of chemical uses for it in addition to all the questionable morality and social functions of ethanol in the real world. I digress. Propanol is 3 carbons with an OH off the end of it. But notice there in the name, there's a 1 in front of it. All right, 1 propanol. And when you get to chemistry, in organic chemistry, the alcohol group, the OH group, is actually really important for chemists. There's a lot of cool chemistry you can do with the OH. The alkanes and the cycloalkanes we saw are basically just good fuels. They don't do a lot of chemistry. But if you have an alcohol and OH on the end of it, there's some pretty cool kind of transformations you can enact. So 1-propanol would be the official name for the compound. You can see it rotating it. Now, there's a new type of naming in organic chemistry. Anyway, and instead of calling it 1-propanol, the new way of calling this is propan-1-ol. And when you get to really sophisticated chemical structures, there is a utility for calling it propan-1-ol versus 1-propanol. You'll see that as you go further into organic chemistry. But again, like all this stuff in Chem 222, I would be pleased if you put down 1-propanol or propan-1-ol. Either one is fine. The reason the 1 is there is because it's off the first carbon. So if you count right to left, OH is 1, 2, 3 right there. You can see then why this one is 1. If you count left to right, it looks like 3. Don't call it that. Smallest number is definitely key. But there's no reason why you couldn't put the OH off the second carbon. You would have 2-propanol or propan-2-ol. Either way is fine. And both of these are quite important. Now, the one on the right, 2-propanol, is also known as isopropanol. And isopropanol is used a lot as a cleaner. You can buy it at Fred Meyer's and stuff like that. So you see 2-propanol quite a bit. 1-propanol you can find too and stuff. But anyway, you can name them either way you want to and stuff. Isopropanol I'm not as excited by, but 2-propanol or propan-2-ol would be fine. Oh, organic chemistry. And again, notice the importance of those isomers. Another thing about alcohols is that sometimes they'll refer to primary, secondary, and tertiary. And this is a little bit weird. But anyway, it is something that does affect the reactivity of the alcohol. And if you see this in a future class, I want you to be aware of how this works and stuff just in case. Ethanol, CH3CH2OH, the OH is connected to this carbon right there. And if that carbon carbon, which has the OH on it, is connected to one other carbon, i.e. one alkyl group, they call it a primary alcohol. So ethanol as well as 1-propanol are considered primary alcohols. A secondary alcohol is actually sometimes a little bit more reactive. And a secondary alcohol means that the carbon with the OH is connected to not just one alkyl group or one carbon, but two of them. So secondary means it has two carbons connected to the carbon with the OH on it. And again, 2-propanol or rubbing alcohol there, isopropyl alcohol, is an example of a secondary alcohol. And finally, you can have a tertiary alcohol, which just means that, again, the carbon with the OH is connected to not one, not two, but 3 carbons, 3 alkyl groups. And this can make a big difference when you get to organic chemistry. See, it's nothing that I will probably be asking you about, but just in the back of your mind, remember that there are these primary, secondary, tertiary, and it's how many carbons are connected to the carbon with the OH, which is a little bit strange. Let's figure out the name of this molecule, all right? And so we're looking at it and we're saying, okay. So first of all, like before, let's figure out longest chain of carbon atoms, because it doesn't matter if it's an alcohol or a cycloalkane or anything like that. You've got to figure out the longest chain. So definitely there are 4 carbons right there. That's going to be the longest chain. That would be butane. However, as you probably saw right away, this is not an alkane. This has an OH group, an alcohol. So it's going to be some type of butanol or butan something all right, which is cool. So butanol is the name. But that OH, you don't have to have on that carbon. You could move that OH around. So you've got to figure out the smallest number. And again, while you're learning, I recommend you count in both directions. So people usually start left to right. First carbon, second, third, fourth. So it kind of looks like it could be 3-butanol or butan-3-ol, answer D. However, count the other way too. So in that case, if you went right to left, 1, 2, 3, 4. So you could also call this compound 2-butanol or butan-2-ol. And you guessed it, longest chain, smallest number, always the winner. Butan-2-ol or butanol, 2-butanol would be the best name for this compound. All right. This is technically a secondary alcohol. The carbon with the OH is connected to 2 other carbons with 1 hydrogen. That makes it a secondary. That's not as important. If you can see the name, longest chain, and then smallest number, I consider it a victory. And again, if you called this 2-butanol, I would be very happy with it. That's not a problem at all. A glycol is a diol. It's an alcohol with 2 OH groups on it. And these are actually somewhat common. So ethylene glycol and propylene glycol are sometimes used as a type of an antifreeze in a car and stuff like that. They are both examples of diols. Ethylene glycol is the unofficial name for what's an ethane with OHs off both the first and the second carbons. So ethane 1,2-diol would be the official name of this compound, but ethylene glycol is what almost everybody calls it. Propylene glycol is a propane, propane, all right? And the alcohols are off the first and second carbons, so it would be propane 1,2-diol. These are just things that you might run into. This is just like 2 alcohols on the same compound instead of just 1 OH like we just went through. And yes, you can have a triol. This is an example of a 3-carbon system where there's an OH off the first, second, and third compounds. So the official name here would be propane 1,2,3-triol. Oh my goodness. But nobody calls it that except nerdy chemists like me. Glycerol or glycerin is the unofficial name for it. And that's what people usually refer to this as. So glycerol, which is the same as glycerin, all right? Just 3 carbons in a row, 1 OH off each of them. Oh, chemistry. An OH is the indicator that you have an alcohol when it's connected to the alkyl group. But instead of an OH, you could have an oxygen with a second alkyl group connected to it. So an ether is when you have an alkyl group with an oxygen in the middle and another alkyl group on the other side. Now, everything in these is tetrahedral sp3. The oxygen is tetrahedral bent because oxygen likes to have two lone pairs to make a formal charge of 0. Ethers are actually really good solvents a lot of times for chemical reactions in organic chemistry. Diethyl ether is a super important organic chemical, and diethyl means two ethyls connected by an oxygen. That's what the ether is, diethyl ether. Diethyl ether used to be a compound that you could go and buy at Fred Meyer's, Home Depot, stuff like that, but now it's a controlled substance. People making meth and different compounds like that, they restrict access to diethyl ether big time. So at Mount Hood, we have like a license. We're an educational research institution, so we can buy diethyl ether, but it's not usually available for just common use, which is kind of sad, kind of funny, kind of interesting, whatever you want to put down. Anyway, ethers, dialkyl ether. All right, so you could have dimethyl ether, which would be an oxygen with a methyl, CH3 on both sides. You could have all different compounds as you go through. However, when I first started teaching organic chemistry in Chem 222, and I asked for feedback for people that went on to organic chemistry, they said, Russell, you've got to start talking about the other way of naming ethers. And I was like, oh, cool, that's good. So if you ever run across something and you said, Russell should have talked about this, you should definitely let me know, and I will try to change my lecture notes as I am right here. So there's an alternative way for referring to ethers, which is definitely gaining more momentum than my old school way. And I'd like to show you both ways so that you're good to go. Just like we saw with the halogen or the alkyl halides, you could call them iodomethane, stuff like that. Well, you can also call them the ethers as an oxyalkane. So if you look at the compound in the first example, there is an ethyl group, CH3CH2 on the left, and there is a propyl group, CH2CH2CH3 on the right. So in the old days, there was an ethyl group and a propyl group where the oxygen was connected to the first carbon. So in the old days, I would have called this ethyl 1-propyl ether. And in my Chemistry 222 class, that's totally fine. However, there is a newer way of doing it, which has a lot of cool uses for it. You look at the shorter alkyl group. So ethyl is shorter than propyl, 2 carbons versus 3 carbons. The shorter name, you call it an oxy. So notice in the name it was ethyl minus YL plus oxy. Ethyl becomes ethoxy, and then the rest of it you call as if it was an alkane. So propyl becomes propane. So you could also call this crazy thing 1-ethoxy-propane. The ethoxy group is off the first carbon of propane. You could move that ethoxy group to the second carbon, and you could have 2-ethoxy-propane. So this is the newer way of referring to these molecules. And again, for Chem 222, either way is fine. I like you to listen to both of them so you get used to it. But in the real world, you might see this newer method more than the other way. The second one has a methyl group, and then there's a 3-carbon system that the ether is connected to. So the OCH3 is connected to the second carbon in a propane. So the OCH3 we would refer to as a methoxy group, shorter number of carbons, CH3 versus propyl. It's off the second carbon in what would be propane if it was just all hydrogen, but obviously it's not. So 2-methoxypropane would be the official name using the newer systems. In the old days, I would have probably called this something like methyl 2-propyl ether. Honestly, I think the newer way is pretty cool, to be honest. I kind of like the 2-methoxypropane. I think it's a little bit nicer than methyl 2-propyl ether, but whatever, I'm pretty fine, stuff like that. And remember, down here, which is a coffee cup a student gave me a long time ago, it's kind of cool. You either get organic chemistry or you don't. Either. Okay. Anyway, my bad sense of humor. All of the oxygens we've looked at so far have been tetrahedral sp3, so they would be bent molecular geometries, stuff like that. But another common combination of oxygen with carbon is to create what's called a carbonyl group. And a carbonyl group, which has a carbon-oxygen double bond, is pretty handy. There's a lot of neat uses for carbonyls in compounds. And so the first example of a carbonyl chemistry compound we're going to look at here is called a ketone. And if you look at the structure in the lower right, the middle part has a carbon-oxygen double bond on it. All right, so this is now an sp2 hybridized carbon. It's got a double bond O and 2 single bonds, so this would be trigonal planar. All right, if you have a carbonyl between 2 alkyl groups, so here's alkyl group number 1, alkyl group number 2. In the picture, it's a CH3 on the left and a CH3 on the right. If you have alkyl groups to both the left and the right of the carbonyl, you have what's called a ketone. And the most famous and common of the ketones is the one that's in the picture right there. You have 1, 2, 3 carbons, which would be, if it was an alkane, propane, but it's not a propane. You take off the E and you add ONE to it, making it propanone. So propanone is a ketone. It has a C double bond O carbonyl in the middle of it, but we call it propanone because 3 carbons would be like propane. Oh boy. But again, you have to have alkyl groups on both sides of the carbonyl to be a ketone. Now, propanone is not a name that's probably familiar to you, and I totally understand. However, propanone has a much more common name, which is acetone. And in the face-to-face version of the labs for Chemistry 221 through Chem 223, every once in a while we use acetone as an agent to dry glassware. Acetone is good about dissolving water. Hardly anybody calls acetone propanone, again, except for nerdy chemists like me, and I also refer to water as dihydrogen monoxide, so this is my world. However, now you know that propanone and acetone are the same thing. So acetone is a chemical you can buy from Fred Meyer's, Home Depot, stuff like that. It's good for taking off things like fingernail polish. Lots of cool uses for acetone, which is technically propanone. A ketone had a carbonyl, a C double bond O, which was connected to alkyl groups on both the left and the right side. So because the carbon is sp2 trigonal planar, you have 2 possible spots, if you will, to put something in, and ketones had alkyl groups on both sides. However, if you place at least 1 hydrogen next to the carbonyl, the reactivity changes drastically. So that's actually a whole separate family of compounds, which is called an aldehyde. And an aldehyde has the same carbonyl, the same C double bond O, but on one side you have at least 1 hydrogen. All right, you might have 2 hydrogens. You have to have 1 though to be an aldehyde. Aldehydes and ketones have the same formula, but the difference is that C double bond O has at least 1 hydrogen next to it. So you've got to be really careful about these. The reactivity is quite different. The simplest of the aldehydes is methanal. If you have a C double bond O with hydrogens on both sides, and that's what the picture is there on the lower right, that is methanal. Methanal, the name comes from methane, which is a 1-carbon system, but because it's an aldehyde, it's given the symbol Al at the end. So methanal is the name of the aldehyde with 1 carbon. Ethanol methanal would be the name of the aldehyde with 2 carbons. You'd have a C double bond O with only 1 hydrogen, and the other side of it would be a methyl group. But methanal is just 1 carbon. So be aware, aldehydes and ketones are very similar. Now, methanal is a chemical name that most people don't use. Most people refer to methanal as formaldehyde. Formaldehyde is used in the funeral services area quite a bit for different things, which I don't understand and don't know about. But anyway, it's some kind of preservative. Anyway, formaldehyde has a lot of cool uses. I guess you can think about it that way. Anyway, it's quite a bit different than ketones. However, both aldehydes and ketones have that carbonyl, so just kind of be aware of it. So let's say we wanted to name this molecule right here. Like, what would you do? Well, again, it comes down to finding longest chain and stuff like that. But we also have to think now about the type of compound it is, because that's going to affect the name quite a bit. So if you count up the number of carbons, there's 4, and the alkyl group for 4 carbons was butyl, so it's going to be bute something, all right? And we've got that C double bond O right there. So C double bond O means it's going to be either a ketone or an aldehyde, all right? It's not going to be an alcohol. And if you look at the answers there, C and D are both OL ending names, and that means they're both alcohols. It's not going to be those. Let's disqualify A as well. Butanoic acid is an example of what's called a carboxylic acid. We'll look at those in a little bit, but we haven't done that yet. So it's not butanoic acid, needless to say. So really this question comes down to the fact, is it an aldehyde or is it a ketone? If it's an aldehyde, you would call the butane, turn it into an al, so butanal, answer B. If it's a ketone, then you take the butane and you add the O-N-E to the end, so butanone. And if you remember from what we just talked about, the aldehydes have an hydrogen next to the carbonyl, the C double bond O. This compound has methyl group on one side and an ethyl group on the other side, but there's no hydrogens right next to the carbonyl. So it's not an aldehyde. This is going to be a ketone. This is butanone. All right, it's a ketone. That C double bond O does not have a hydrogen to the left or the right. It's got alkyl groups. So that makes it a ketone, not an aldehyde. Oh joy.